Welcome. In this video, we're going to build upon what we've already discussed and covered to build a table of common antiderivatives. This first one is already done for you, and if you recall, the derivative of big F of x is equal to little f of x, and because of this we can say that big F of x is the antiderivative of little f of x. So let's start with this one, and this one, since they were discussed directly in example 1. The antiderivative of 1 over x is equal to the natural log of the absolute value of x plus c. The derivative of e to the x is just itself, so the antiderivative of e to the x is itself plus a constant. And of course the antiderivative of secant squared x is tangent of x plus a constant. Now we can look at x to the n, so we're undoing the power rule here. And if you recall, we did this in a previous example, in example 1. And if you haven't seen this yet, please check out the video that is linked. In example 1, we saw that if f of x equals x cubed, then big F of x equals 1/4 times x to the 4th plus c. So the antiderivative of little f, which is x cubed, was big F, which was 1/4 times x to the 4th plus c. So let's take a moment and examine what happened here. Well, our exponent was a 3, and we increased it by 1 to make a 4. But not only that, we multiplied by the reciprocal of that new exponent here. So let's try this. That tells me if little f of x equals x to the n, and careful, if x equals -1, then you're in the case where you just have 1 over x, so you're here. So be careful not to accidentally use this trick if you have x to the -1 power. Anyways, back to the task at hand. So if little f equals x to the n power, then we know that big F of x has to equal x to the n plus 1 power, and we need to multiply by 1 over this number, so the reciprocal of that exponent plus c. And a more concise way to write this without taking up so much space is just writing it as x to the n plus 1 power divided by n plus 1 plus c. So that's our antiderivative that will go here in the table. Now let's look at cosine and sine, and let's quickly look at a trick that I taught you all in class. So we'll rewrite sine, cosine, and if we're taking derivatives, we go down in this direction, and let's make this negative and this negative. This tells me that the derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of negative sine is negative cosine. The derivative of negative cosine is sine, and so on. Now, if you're finding the antiderivative, we go up in this direction. So let's start with cosine. So cosine has an antiderivative that is equal to sine x. And we need to add our constant. And now let's look at sine here. Sine is here, and when we go up, there's nothing there, so we go all the way back down to the bottom, and that tells me that the antiderivative of sine is negative cosine of x plus c. All right, finally, there's one more that is left. I'll do this one in blue. So recall, earlier in the semester, before we went on lockdown due to COVID, we did this little project in class where we had everyone figure out, using limits, what these derivatives were, limits and identities, and we figured out that the derivative of secant of x is equal to secant x times tangent x. In that case, that tells me that the antiderivative of secant tangent is secant x tangent x plus c.